Today we're going to talk about lesson 1-4, picturing expressions. What we're going to look at is graphing expressions on a graph and understand the relationship in between your x value and your y value. Now, if you remember how to graph points, okay, coordinates are in x comma y. Therefore, you graph the x value first, which goes from left to right, depending on if it's positive or negative, and y goes up or down. So, if I ask you to graph 1, 2, you would go 1 unit to the right and 2 units up, and you would get your point. That should be a little bit of review for you. In activity 1, in lesson 1-3, when we talked about the toothpicks, discuss this toothpick sequence. We had the first term had 4 toothpicks, 2 had 7, 3 had 10, 4 had, etc. Suppose a student looks at each instance as 1 vertical toothpick on the left and 3 more toothpicks being added for each additional space. So they saw it as there was 1 toothpick, and then for the first term, they added 3. For the second term, they added 3 twice. For the third term, they added 3 times. And for the fourth term, which is down here in this case, they added 3 of them 4 times. So this student came up with the expression 1 plus 3n to describe the sequence. Scatter plots. The table shows values for the term number n and for 1 plus 3n, the number of toothpicks in the nth term. Each row can be written as an ordered pair. These pairs then can be graphed on a coordinate plane. So if you notice, my first term had 4 toothpicks. Therefore, the coordinate is going to be 1, 4. The second term had 7 toothpicks, so its coordinate point is going to be 2, 7. Third term number had 10 toothpicks, 3, 10, and then it's going to go so on and so forth. So we could find term number 10 and how many toothpicks just simply by putting it into this expression. 3 times 10 is 30, plus 1 is 31. So essentially we could graph 10, 31. Every point in the plane on the graph can be identified with coordinates. A graph like this in which individual points are plotted is called a scatter plot. And we're going to look at that on the next page. It says, if the points on the graph had been connected with a line, then the numbers between 1, 2, 3, and 4 would be allowed for n. And therefore, the numbers for 1 plus 3n between 4, 7, 10, and 13. Okay? If you look here, they plotted those points that we just got done talking about. 1, 4, 2, 7, 3, 10, 4, 13. If we wanted to, we could have plotted 10, 31. But what you need to know is when we're talking about term numbers, and it kind of says it right down here, when we talk about term numbers, there is no 3.5 number. Our term numbers go 1, 2, 3, 4, 5, etc., etc. There is no 0, and it can go up as high as it wants to as long as it's going up by these numbers. Okay? We do not include 4.7, so on and so forth, 9.8. It always has to be a positive integer. So, the term number is what we call the domain of the variable. What the domain of the variable is all the values that may be meaningfully substituted for a variable. You're going to want to write that down. It's all values that may be meaningfully substituted for a variable. Okay? So in this toothpick sequence, the domain is the set of positive integers. Okay? Positive integers are 1, 2, 3, 4, etc., etc. Notice we do not include 0. Connecting graphs. When writing expressions for real-world problems, you often must decide what domain makes sense for a situation. Okay? This domain here made sense because all we had were term numbers. Okay? If you look at example 1, it says, suppose Rebecca drives to her grandmother's house, which is 500 miles away. Her average speed is 65 miles per hour. Okay? Fill in the table of values to calculate her remaining distance after each hour. So, write an expression to represent her remaining distance and then plot the points on the graph. So at 0 hours, how far is she away from Grandma's house? Well, she is 500 miles away. So, after she drove an hour, she is now 65 miles closer. So, 500 minus 65, you're going to tell me is 435. And all I did was subtract 65. To go from the first hour to the next hour, we got to subtract another 65. You're going to tell me is 370. You're going to subtract another 65, which is 305. And you're going to subtract another 65, which means you are at 240. Oh, sorry, that's H. My bad. Okay, so for H, okay, this is going to be our expression. Each hour we're losing 65, right? So my expression is going to be I'm 500 miles away minus, and how many miles do we subtract every hour? Because that's what my H is. I subtract so many miles per hour. How many miles do I subtract per hour? Well, I subtract 65. Yeah. This has to be negative because we want 500 miles to go down, correct? You start at 500 and you want it to go downwards by the time you get to Grandma's house. Okay? So, if you notice here, they plotted the points for us. 0, 500, 1, 435, 2, 370, okay? So on and so forth. Notice they connected the dots, okay? They connected the dots. Now, why did they connect the dots? They connected the dots because you can drive only a half an hour. What if it's 3.5 hours, 3.25 hours, etc., etc.? You could drive 3.1 hours. Stopping, get gas, go inside, get a drink, whatever. But those fractions occur in this case. This is a real-world problem. Okay? You can drive 3.7 hours. Okay? That is why we connected those dots. Are common domains of variables. The following domains are frequently used in arithmetic and algebra. Okay? Whole numbers. Whole numbers include 0, 1, 2, and 3. Okay, etc., etc. 5, 16 divided by 2 is actually 8. 2007, 7 million are all whole numbers. Integers. Integers are your whole numbers and their opposites. So, all your positive numbers from 0 to all the way out there, and your negative numbers from 0 all the way out there. Negative 21 all over 3 is a negative 7. Negative 17 and a negative 1,000 are all integers. Real numbers. Real numbers is a set of all numbers. Okay? It's any number that you can think of. They can be represented as terminating or non-terminating. Okay? A terminating decimal would be like 0.25. A non-terminating decimal would be like 0.13 repeating. That will never stop. Okay? Real numbers include every single number in mathematics. Non-negative real numbers. Okay? This is what we call set builder notation. Okay? It's the set of x such that x is greater than or equal to 0. Is the set consisting of 0 and all positive real numbers. Okay, so that's how we say non-negative real numbers. Okay, because there's going to be certain times in our real world situations where we're just going to be using the positive numbers, real numbers. Down here below tells you a little bit more about the set builder notation. Please, I would like for you to read that and make sure that is in your notes. Thank you very much, and we'll see you tomorrow.